So if you have a handle on what a complex number is, let's look at what sort of mathematical operations we can do with them and how we go about that. So if we have two complex numbers and we're trying to add them, what we do is we take the real parts, the real part of the first one and the part of the second one, and add them. And we take the imaginary parts of the two numbers and add them together. What we're doing is combining like terms. If we have a complex number times some lambda, some real number, lambda, some scalar, we're taking the real part, multiplying it, and the imaginary part and multiplying it. What we're doing is we're distributing. Hopefully you're saying, oh, that's not new. I can do that. That's not so bad. What about multiplication? What if I have two complex numbers, I want to multiply them, and I have a1, b1i plus a2, b2i? What do we do there? Well, looks an awful lot like a situation where we'd do a little bit of that action. A little bit of foiling, ladies and gentlemen. So, a1, a2, that's the f part of FOIL, plus a1, b2 times I, plus a2, b1i, plus b1, b2, I squared. Now, there's some cleaning that we can do here. A1, A2, plus, now these two things both have i's, so it's going to be A1, B2, plus A2, B1, quantity times I, plus, now there's something magical that we can do right here. Remember, we define I to be the square root of -1. So, guys, what's I squared? I hope you're saying I squared is going to be -1. Okay, so forget this plus business here. What we're really doing is we are subtracting b1, b2. Anytime you see an I squared in your algebra with complex numbers, you need to replace it with -1. So the real part of this is a1, a2 minus b1, b2 plus the imaginary part would be a1, b2 plus a2, b1 times I. And this is a lot easier in practice if you actually just multiply the two complex numbers the way I did with these letters here when you come to an actual problem, like we're going to do right now. So here we have three complex numbers. I want to multiply them together and then take z1 times z3 minus 3z2. So go ahead and try to do this multiplication right now without me. Try to do 2 plus 3i times 3 minus 4i. Go. All right, so let's see how you did. 2 times 3 is 6 minus 8i plus 9i minus 12i squared. Now we simplify. Combine like terms, we've got 6 plus I plus 12. Remember I squared. What's I squared? I squared is -1, so this minus 12I squared becomes plus 12, and our finished product will be 18 plus I. When you multiply or add or subtract or even divide, you are going to get a new complex number. Please remember that as you're going. All right, so the second one, hopefully you've attempted this one also. 2 plus 3i, 1 minus I, minus 3 times 3 minus 4i. I'm going to multiply the first two together and distribute into the next one. 2 minus 2i plus 3i minus 3i squared minus 9 plus 12i. Now we start cleaning. Combine like terms. 2 minus 9 is -7. And we have these I terms. So we have plus 13i. And then what happens with the minus 3i squared? You better be saying you add 3. So my final complex number for this expression is going to be -4 plus 13i. Okay, so now we have an equation we're going to solve. There's some mystery unknown complex number z where 4 minus 2i times that z is equal to 3 times z plus 2 minus 5i, where z is a complex number. Ooh, wow. That looks intense, man. That's crazy. That's crazy talk. Well, let's do this. How about we do 4 minus 2i? And instead of calling it z, let's use a plus bi. Equals 3 times a plus bi minus 2 minus 5i. What we're going to do here is we're going to take the left side and find the real and imaginary parts. And we're going to take the right side and find the real and imaginary parts. And then we're going to set them equal to each other. So let's expand the left. We have 4a plus 4bi minus 2ai minus 2bi squared equals 3a plus 3bi minus 2 plus 2 minus 5i. Now let's clean it up. Remember, minus 2bi squared, I squared is really negative 1, so that's really plus 2b. So 4a plus 2b. Those are the two pieces that don't have I in them. Plus 4b minus 2a times I. So real part, imaginary part, equals 3a plus 2 plus 3b minus 5 times I. So we have real part equals real part, and imaginary part equals imaginary part. If these complex numbers are going to be the same, if this is an equation, the reals have to equal the reals, the imaginaries have to equal the imaginaries. So let's set up a system. 3a plus 2b equals 3a plus 2. Okay, cool. For a plus 2b. And similarly, 4b minus 2a equals 3b minus 5. Let's get these written how we're used to seeing it. We have a plus 2b equals 2. I subtract 3a from both sides. And the second equation would be negative 2a plus b, I'm subtracting 3b from both sides, equals negative 5. Ooh, now that looks like something we can handle, right, guys? You better be saying yes, otherwise I'm really sad. Take the top equation, multiply by 2. Now we have 2a plus 4b equals 4. I'm using elimination here. You guys could have used substitution. Doesn't matter. We add these buggers together. The a's become nothing. We have 5b equals negative 1. So b equals negative 1/5. Now what do we do with negative 1/5? We take that and we substitute it back into one of these other original equations. I'm actually going to go into the top one, a little bit more efficient because a is by itself. So a plus 2 times negative 1/5 equals 2. So we have a equals, if we solve this, 12/5. But wait, that's not the answer, guys. Sorry. Tough luck. We're not done, but we're almost done. I wanted z, not a and b. So z is equal to a plus bi, or a minus, since b is negative, 1/5 I. There's my new complex number. So conjugates. What the heck is a conjugate? You probably have heard this word before. We use it with radicals But the conjugate of a complex number, if the complex number is a plus bi, the conjugate z star is a minus bi. We change the sign between the real and imaginary part. It is not the same as the opposite of z. So what's z plus the conjugate? A plus bi plus a minus bi, that's going to be equal to 2a. How about z minus the conjugate? That's going to be 2bi. What if we multiply the conjugates together? Well, here we're going to have a plus bi times a minus bi. And well, if you look at that, that looks like the factorization for a difference of squares. So this is a squared minus bi squared, which would be a squared minus b squared I squared. But I squared is negative 1, so this is a squared plus b squared. Notice in these two here, the imaginary part goes away. In the middle one, the real part went away. And we're going to use this conjugate idea to help us with dividing by complex numbers.